welcome to the last, as far as I know, the last video in my tutorial series on Python for physics educators. And maybe you're a physics student and that's cool too. The playlist is linked down below. So I'm going through the second semester of the calculus-based physics course and showing some cool Python stuff that students could do, or you could, as an instructor, use as a demonstration in your class. And I'm going to end here with the LRC circuit because it's awesome. So let's just get to it. So the first thing that we have is an inductor. An inductor is a coil of wire, and it turns out that if I have current running through this coil, it's going to make a magnetic field. But if I have changing current in this coil, it's going to make a changing magnetic field, and the changing magnetic field makes an electric field. That's Faraday's law. And that electric field opposes the change. So that means that if I have this coil of wire, which we call an inductor, then the voltage across it can be written as this. The voltage from one side to the next is going to be negative L di dt. So the rate of change, the derivative of the current. So if current is constant, the voltage is zero. The faster the current changes, the greater the voltage. And L is the inductance. It's a property of the coil itself. Next, we have the capacitor. And I already did a video on RC circuits. So a capacitor also has a voltage across it depending on the charge on the capacitor. So I can write this. The change in voltage across the capacitor is Q over C. And so in this case, if you have a constant current, then the charge is going to build up and this is going to build up. And so these two things act differently, right? This one doesn't like changing current, quote, change in currents, and this doesn't like constant currents. If you have a very high rate of change of current, this one's going to have a high voltage. If you have a constant current, this goes to a high voltage. So when you put them together, that's when cool things happen. Okay, we're going to start off with a simple circuit like this. So I'm going to have a capacitor that's charged that's at 3 volts, and then I'm going to close the switch. And what's going to happen is when I close that switch, there's no currents, there's essentially no resistance in the wire, and you would get an infinite change in current, which you can't have because then that's going to make a voltage across this. So this is going to actually produce a voltage that's going to be greater than 3 volts, or at some point. And so this will charge up the inductor, and then that will discharge back into the capacitor. So you get an oscillating circuit, and that's what I want to show. Oh, I'm going to go ahead and say this. I'm going to build this, and then I'm going to add a resistor, and then I'm going to add a power supply. Omega equals 1 over the square root of LC. That's the frequency of oscillation that we should see. Okay, let's just go ahead and start off with this. I want to start off with the loop rule. This says that if I go around the loop, the total voltage has to be 0. So let's go this way, and I go across the capacitor. If I do that, I get a voltage drop of a positive voltage of delta VC, which is Q over C. So I can get Q over C. That's the voltage across that capacitor. Now I'm going to go across here, and I get the voltage across that is going to be minus L di dt. And then I get back to where I was, and that's 0. So here I have Q and I have I, but it turns out that I is the rate of change of charge. So I can put I as dq dt. So this is going to be Q over C minus L times d dt of dq dt equals 0. And so I can write that as Q over C minus L, the second derivative of Q with respect to t equals 0. Now I can solve this for Q. Actually, what I want I want to solve this for dq dt. So let's add that to the other side and divide by L, and I get the second derivative of Q with respect to t is going to be Q over LC. Is that right? Yeah. Negative. No. It should be positive. Yeah, I think that's right. I always make a sign error here, so that's cool. Okay, so what I'm going to do is, if I know the second derivative of Q, I can calculate that for some value of Q, but Q changes according to this. So you see here we have a complicated differential equation. You can actually solve this differential equation by guessing. It's not too terribly difficult, but I'm going to solve it numerically. So numerically what I'm going to do is to calculate the second derivative of Q using this equation for some short time interval. And during that short time interval, let's say delta t equals 0.001 seconds, I'm going to assume Q is constant, which is not. But if I do assume Q is constant, I can calculate the second derivative as a number. And then I can say this. I can say, once I know that, I can then say delta Q over delta T. No, let's call this, let's say, I'm going to call that Q double dot. Q double dot is dq dt, the second derivative. And that's equal to the first derivative, the derivative of the first derivative. So I'm going to say that is delta Q dot over delta T. If I know this value, which I just did, I can use that to calculate the Q dot at the end of the time interval. So I can say this is Q2 dot minus Q1 dot over delta T. And then I can solve that for Q2 dot. Q2 dot equals Q1 dot plus Q double dot delta T. So I calculate Q double dot from this equation. I use that to find the new Q2 dot. If I know Q1 dot. Okay, I have to know Q1 dot. I have to know the initial rate of change. But now I can do the same thing with Q dot. Q dot is delta Q over delta T. So I can say Q2 equals Q1 plus Q2 double dot delta T. So I just, not double dot, single dot. I just calculated Q2 dot. I'm going to use that down here, assuming it's constant, even though it's not, to calculate Q2. And then I just go back up here. Now I have a new Q, and I can redo the whole thing. Okay, so this is the idea behind the Euler method of a numerical calculation. Okay, now I do make a sign error here every once in a while. Let me just double check really quick so I don't make that sign error. If I do, I do, and that's cool. Okay. Yeah, see, I do have a negative. I have this as negative. If I go from here to there, that's positive. And then if the current is flowing this way, yeah, so this would be, I think this is going to be negative. And I'm not really convinced myself of that yet, but if it works, it works. Okay, so I'm going to calculate the second derivative of Q, and then I'm going to use that to update dq, and then use that to update Q. And so what do I use for my first dq? Well, it's 0, right? This is the current. This is actually the current. Okay, let's just jump over here to Python and make this stuff happen. Python on. Okay, here we are. I'm using GlowScript v Python. Let me make it a little bit bigger. We're going to make a graph, obviously. I'm going to make a graph of, what do I want to graph? What's the best thing to graph? I'm going to make a graph of Q versus T. Okay, so let's say G1 equals graph. X title equals time in seconds. Y title equals Q in coulombs. And I'm going to do this. Width equals 400. Height equals 200. Now the thing I'm going to plot, I'll call it F1 is G curve. Color equals color dot blue, just for fun. Okay, now I need some values for my capacitor and my inductor. So I'm going to say, I'm using the thing I had before. I'm going to say the capacitance is 5 millifarads. C equals 5 times 10 to the negative third. Inductance is 300 millihenries. 300 e negative 3. V0 is 3. So I can calculate Q0. I do need that. And I'm just going to call it Q. Okay. I'm just calling it Q because this is a value that's going to change. So Q is going to be equal to C times, C times V0. That's my initial charge. I also need my initial rate of change of charge. I'm going to call that dq, and it's going to be 0. And then I need t equals 0, and dt equals 0.001. I think that's small enough. Let me see what I used before. Yep. Okay. So now we're ready to calculate some stuff. So I'm going to say, let's just do this for 2 seconds. While t is less than 2, I'm not going to do a rate because I don't really care how long this animates. The first thing I'm going to do is calculate the second derivative of the charge. dq, I'm calling that. And that's just going to be equal to negative q divided by L times c. That's just straight from that thing. I just calculated that. Now I'm going to use that to update dq. So I can say dq equals dq plus ddq times dt. And you'll notice here that in line 15, you can see that that's not an algebraic equal sign. Otherwise, dq and dq would cancel. It's a make equal to sign. Now I can update q. Q equals q plus dq times dt, and update time. T equals t plus dt. If you don't do that, it goes on forever. Now I can plot f1.plot t q. And let's see if this sucker works. It worked. Ha! Sometimes these things don't work. You know, that minus sign thing messes up and so forth. Let's print out the frequency. So the frequency is going to be equal to f equals 2 pi divided by, or times omega, right? So let's say omega is equal to 1 divided by the square root of L times C, and this is going to be 2 pi, let's see, radians per second. It's going to be omega divided by, so it's going to be omega divided by 2 times, let's print the period. T equals 2 times pi divided by omega. That's how long it takes to make one complete oscillation. I can look at that on the graph, and let's print that out. I'm just going to print it as T. So I get 0.24. So if I go up here and to the next thing, it is 0.24. That's how long it takes. So this is important because this agrees with the theoretical calculation of the period of oscillation for a ideal oscillator. This is an ideal oscillator. Okay, now let's add a resistor in there. So I'm going to go ahead and say R. R equals, what did I use before? I want to use the same value I'd used before. Let's use R equals 3 ohms. And let's look at real quick what we need to change in order to make that happen. So if I add a resistor, now my circuit looks like this. I'm going to put a switch there just so you know that there is a switch. So if I do the loop rule again, I'm going to get Q over C minus, now I have this as I, minus IR, and it is plus, let's see, I keep making dumb mistakes. Actually, I have plus L second derivative of Q with respect to T equals 0. I'm not sure why that's plus. Q, I think, okay, here's the problem. Because I is the rate of flow of charge, but this is the charge on the capacitor. So these two things should be opposite. If I was positive, it would increase Q, but I don't want to do that. I want I to decrease Q because the capacitor is being discharged. But either way, I can write this as the following equation. Q over C plus Q dot R, right? That's dq dt, plus L Q double dot equals 0. Now I want to solve this again for Q double dot. Let's see if I get this right. So Q double dot is going to be equal to negative Q over LC minus Q dot times R over L. Is that right? Yeah, that's right. So now instead of just saying this, that's what I had before, I have this extra term. That's pretty easy to add in there. Okay, so let's just do that. Let's modify our code, switch back to Python. And all I need to do is add that line in here. So I'm going to say minus Q dot, which is dq, times R divided by L. And let's run it. So with the resistor in there, every time it passes back and forth, the total current decreases a little bit, the total charge in the capacitor, because that resistor is dissipating stuff. If I make the resistance smaller, let's make that 0.5, I can run it and it dies down slower. If I make that resistance higher, let's say 5, it dies down faster. Pretty easy, right? Okay, now let's put that back at 3. What if I add a power supply, an oscillating power supply, to my LRC circuit? So let's draw that out just so you can see what it looks like. So I'm just going to put right there, I'm going to say V equals V0 cosine omega 1 t. So that's an alternating power supply. So all I have to do is add that in here. So I'm just going to put V0 cosine omega 1 t plus. And I think it's okay. It doesn't really matter. So when I solve this for dq, I'm going to get that on the other side, and I get minus V0 cosine omega 1 t, not dt, t. So let's add that in there. And I need to pick a frequency for my power supply, and I'll use the 3 volts right there. Okay, so switching back to computer view, Python. Let's say I got V0, so I'm just going to go over here and say minus V, I need omega 1. W1 equals, let's say 1 hertz. Because the other one had it had a period. It had a period of 0.2. So divide by that before. So let's say 10. I don't know, I'm guessing. So it's going to be V0 times cosine omega 1 times t. That's it. That's all I'm doing is adding that in there. And you see, it's working, right? So we get this weird oscillation thing at the beginning, but then it actually settles into some constant oscillation. Now, notice here the amplitude of 0.9 volts. No, that's the time. 5 times 10 to the negative third. What if I put this at, let's print omega 1. Let's print omega. Oh, that is omega. No, that's t. Let's print omega. So 25. Okay, let's increase this to 15 hertz, the 15 radians per second. And you'll notice that the voltage is now 6.3 times 10 to the negative fourth. Let's increase this to 20. Now that voltage is getting bigger. Now let's do 23. It's getting bigger. Let's do 25. So this is what we're doing is building a resonance. This is a resonant circuit. You'll notice here that I have a much higher voltage of 1 times 10 to the negative 2, which is higher. If I make it too high, it again drops back down. Let's just jump up to 50. There it goes, dropped right way down. So this is how a radio works. The resonant frequency depends on L and C. If you get it at just the right resonant frequency, you can have a larger amplitude of oscillation, and that's how you tune those radios for an analog radio. But I don't want to get into that too much but it is cool just to play around with that. Okay, so saving this, let me save this. Did I save it? No, I didn't even save it that whole time. LRC circuit example. Okay. The code is down below. A link to the playlist is down below. You know, I'm making a lot of other videos. It's just these are the videos that I want that I would put in an introductory course that I think are introductory level videos to learn Python. But if you have requests on other things, just leave a comment or send me a message or whatever. I'm going to make a whole bunch more videos, but I feel happy making that complete package. It's a pretty long playlist. It's probably too long, but I couldn't help myself. So there you go. Hope you enjoy yourself with it. Let me know if you have any questions. I'll be here for you, and I'll talk to you later.